We're going to go back in time. Think back to your 4th grade math class. Can you picture your 4th grade math teacher? Do you remember what you did? Do you remember drawing parallel lines, line segments, angles, rays, and perpendicular lines? Now go forward a few years. You're in 7th grade and you're learning the formulas for the area and the circumference of a circle and using them to solve problems. Picture yourself working out the relationship between the circumference and area of a circle. Okay, let's come back to your high school geometry class. We're going to work with some of the same geometric concepts that you worked with when you were younger, but this time you're old enough to understand the precise definitions. So by the end of the day, you will know the precise definitions of parallel line, line segment, circle, angle, and perpendicular line. Once you have these basics down, you will be able to start studying Euclidean geometry. Euclidean geometry will help you think more logically. The ability to think logically will help you make better decisions in all sorts of areas of your life. Because it's always better to base decisions on logic rather than biases and emotions. Just think if next Tuesday all the voters used logic rather than their emotions, and what a wonderful world we could have. Let's start by defining parallel lines. Two coplanar lines are M and N are parallel lines written this way if and only if they have no points in common or they are identical. I'll show you 3 examples of parallel lines and 2 non-examples. Here's our first example of a parallel line. We have 2 lines M and N. We can write line M in the standard form, and then we can write N in the point-intercept form. Notice that we can rewrite M so that we then find out that they're identical lines and that they're coplanar. Thus, by definition, they are parallel. Here's a second example. We have 2 lines L and M in the XY plane. These lines have the same slope, but a different y-intercept, and they can be written this way. Notice, they will not intersect, but they're in the same plane, so by definition, they are parallel lines. So here is our third example. Notice how these 2 lines do not share a point, and they are coplanar, but in a plane that intercepts plane XY. Here are 2 non-examples. The first example shows 2 lines that are not coplanar. The second example shows 2 coplanar lines that have a point in common, yet the lines are not identical. Thus, these cannot be parallel lines by definition. Our next definition is the definition for a line segment. The line segment with endpoints A and B, which we can denote in this way, is the set consisting of the distinct points A and B and all the points between A and B. I'll show you 3 examples of line segments and 2 non-examples. Here's our first example. So, for all points x that are in the set of real numbers, and where x is less than or equal to 100, and x is greater than or equal to -5, we can write it like this as a line segment, because it is the set of all points representing real numbers between and including the distinct points -5 and 100. It could be drawn like this. Here's a second example. Here's a triangle with 3 sides drawn in the coordinate plane. Each of its sides is a set of 2 distinct points, and all points between them. Thus, the triangle has 3 line segments. Third, if you graphed y equals 3x plus 1, where x is greater than or equal to negative 10 and x is less than or equal to 2.5 on the xy plane, then the result would be a line segment, because it would be the set of points between the distinct point coordinates negative 10, negative 29, and 2.5 and 8.5. Here are two non-examples. This is not a line segment, because it is a ray. Rays only have one endpoint. This is not a line segment, because it is a line. Lines don't have endpoints. Our third definition will be for a circle. A circle is the set of all points in a plane at a certain distance, its radius, from a certain point, its center. Here are three examples of circles. This is a circle with radius 2 and center 0, 0, and all of its points are in a plane together and are just 2 units away from its center. This is a circle with radius 6 and center in a three-dimensional coordinate system of negative 1, negative 1, negative 1. All of its points are in the same plane and are 6 units away from its center. This is another circle with radius 6, but in a different plane. Here are non-examples of circles. This is an ellipse. While it is all the points are in the same plane, the points are not all the same distance from its center. A circle has points in the same plane that are all the same distance from its center, which is called the radius. This is a sphere. While all the points are the same distance from its center, they are not all in the same plane, and we know that a circle needs to have all of its points in the same plane. Our fourth definition is angle. An angle is the union of two rays or line segments that have the same endpoint. Here are three examples of angles. Here is an example of two line segments that share the same endpoint and whose union forms an acute angle. That's less than 90 degrees, you'll probably remember. Here's an example of two rays that share the same endpoint and whose union forms an obtuse angle, which you'll remember is greater than 90 degrees. Here is an example of two rays that share the same endpoint and whose union forms a right angle. Here are two non-examples of angles. These line segments do not share an endpoint. Since an angle is the union of two line segments or two rays that share the same endpoint, this cannot be an angle. This is just a ray. An angle is the union of two line segments or rays that share the same endpoint. Our final and fifth definition is for a perpendicular line. Two segments, rays, or lines are perpendicular if and only if the lines containing them form a 90-degree angle. Here are three examples of perpendicular lines. These two line segments that form the adjacent sides of a rectangle are perpendicular because the sides of a rectangle are at right angles to each other, or, in other words, 90 degrees. Thus, the lines containing the line segments of a rectangle form a 90-degree angle. Therefore, the sides of a rectangle are perpendicular. Here's another example. A ray defined by the set of coordinate points that are a set of real numbers where x is equal to 1 and y is greater than or equal to 0 is perpendicular to the x-axis in the coordinate plane because the lines containing the ray forms a 90-degree angle with the x-axis. the two lines, y equals 2x plus 5 and y equals negative 1/2 x plus 5, are perpendicular because the lines that contain them form a 90-degree angle. Here are two non-examples. Two line segments forming an acute angle are not perpendicular because the lines that contain the line segments form an angle less than 90 degrees. Two rays that form an obtuse angle are not perpendicular because the lines that contain them form an angle greater than 90 degrees. So there you have it. By now you should be able to give the precise definitions for parallel line, line segment, circle, angle, and perpendicular line. You will need to know these precise definitions and take some time to master them, because we will be using them in the next week to develop definitions of rotations, reflections, and translations. Good luck. You can do it.